This section is about Newton's second law, deceleration and force reduction. So, imagine that you're falling at high speed towards the Earth, whether in a spacecraft or not. When you hit the ground, you'll want to minimise your force of impact to maximise your chance of survival. To minimise the impact force, we need to look at Newton's second law again. That's force equals mass times acceleration. Or in this case, force equals mass times deceleration. That is negative acceleration, causing velocity reduction. To minimise the deceleration needed, and therefore the impact force, we can do two things. One, reduce the velocity before hitting the ground, therefore the deceleration needed on impact and thus the force experienced is reduced. For example, use a parachute or reverse thrust. The second thing we can do is to transfer the force so that something else absorbs the impact and your deceleration is reduced. Examples of this are the crumple zone of a car or airbags. They work by increasing the time over which you are slowed from high velocity to zero velocity, thus decreasing your deceleration and therefore the force on you. Landing on something soft like a giant pillow, cushion or trampoline will also have the same effect. An extreme example of what happens when things are not slowed down is a meteor colliding with the Earth's surface. The force required to decelerate them is considerable since they are moving quickly and can be quite large. Their capacity for destruction is therefore huge. A well-preserved example of this is the 1.2 kilometre wide Barringer crater in the Arizona desert. A more recent example is the 1908 Tunguska event in Siberia, where it's thought that a meteor exploded just above the Earth's surface, and the force of the explosion knocked down 80 million trees over an area of 200 square kilometres. Now let's think about the same thing in reverse, hitting an object to make it move. For example, hitting a golf ball with a golf club. We can use conservation of momentum, momentum before equals momentum after, to calculate what happens to the ball in the moments after it's struck by the club. But what happens in the short time that the golf ball is in contact with the golf club? In this very short period of time, the club puts a very high force on the ball to accelerate it quickly to a high speed. We call this an impulsive blow. And from this we get a quantity called impulse, which is the integral of force with respect to time, or just force times time if the force is constant. This expression for impulse is another way to write Newton's second law, in the same way that an equivalent expression to force equals mass times acceleration is force equals change in momentum divided by time. This implies that impulse is just change in momentum. The bigger your impulsive blow, the faster your golf ball goes. A way to visualise this is using a graph of force against time. The area under the graph is the change in momentum. If we compare these two graphs of two different impulsive blows, they both have the same area underneath, the same impulse. Therefore, an object will have the same velocity at the end of each blow. Which graph do you think is most representative of a golf club hitting a golf ball? Now imagine replacing the golf ball with an egg. Which blow would be most likely to accelerate the egg whilst leaving it intact? Now imagine replacing the golf ball and the club with you in an aeroplane accelerating down the runway. Exactly how would you like to be accelerated to a takeoff speed of 150 miles per hour? Which graph would you like to be applied to you? We reduce the force of impact by increasing the time over which an object is accelerated or decelerated.